Well, thank you very much. It's great to have the opportunity to talk to you about PAHs, our database, and what it could do for JWST data analysis. I'm Christian Boersma, and I'm the lead on the NASA Ames PAH infrared spectroscopic database. The outline of my talk is as follows. I'll start with a quick background on polycyclic aromatic hydrocarbons, as we heard PAHs for short. This will be followed by an overview of current PAH spectral databases, and then finishing up with a dive into database fitting. So first, PAHs. The infrared spectral signature of the class of chicken wire-shaped molecules known as PAHs is omnipresent throughout the cosmos, and J.D. Smith alluded to that as well. And as the images here demonstrate, this signature is observed from solar system objects, from many interstellar medium sources, from galaxies as a whole, and even outside galaxies. And some of these pictures are truly gorgeous. JWST will capture the infrared universe with unprecedented sensitivity and spectral spatial resolution. Most JWST observations will contain the PAH features. Interpreting them, therefore, properly will be really essential. Besides being responsible for producing some of the gorgeous images we just saw, the relevance and importance of astronomical PAHs cannot be understated. And here are a few listed, and some of them might repeat what JD said, but it's important to repeat those. So up to some 30% of the total infrared emissions is carried by PAHs, and they lock up some 10 to 30% of the cosmic carbon. PAHs play an important role in the energetics and chemical processes in the interstellar medium. PAHs are the largest and most complex carbon-containing class of molecules known in space. They are more abundant than all other interstellar polyatomic molecules combined. PAHs are found in meteorites and extraterrestrial interplanetary dust particles. PAHs represent the single largest source of biochemically accessible carbon available in the early solar system, so that's a connection possibly with early life. And PAHs trace the first appearance of carbon in galaxies on cosmological timescales. Obviously, the astronomical community has taken note, and the rate of PAH-related papers being published has been steadily growing, with a considerable increase with the launch of Spitzer. Though seemingly still increasing year over year, the rate flattened off to the pre-Spitzer level around 2014. With Webb, of course, we expect to see another big jump. So what are PAH spectral databases and what can they do for astronomers? PAH databases typically hold laboratory measured and/or quantum chemically computed PAH spectra, with each method of acquiring the spectra having its own advantages and disadvantages. For example, laboratory measured spectra contain overtone and combination bands, which are typically not available in the theoretical spectra. This is illustrated in the figure, highlighted by the red bracket, which compares the laboratory measured and quantum chemically computed harmonic spectrum of the PAH coronine. Here is its structure. Also, laboratory measurements open up opportunities for discovery. One example here would be the unexpected presence of electronic transitions found in the mid-infrared for some families of PAHs. A disadvantage of laboratory work is that one is limited by what is available and any potential toxicity. You don't want to poison your lab scientists. For the quantum chemically computed PAH spectra, one obtains all vibrational modes, which is useful when considering PAH emission models. A disadvantage here is that the computations are typically done using the harmonic approximation, which doesn't produce those overtone and combination bands we mentioned earlier. Also, computations can overestimate the strength of the 3.3 micron band. Lastly, it should not be overlooked that laboratory measured spectra are needed to calibrate and hone the theoretical computations. There are currently a small number of PAH spectroscopic databases one could turn to. One's in Europe, the other one at NIST, and the last, the NASA Ames PAH infrared spectroscopic database. Since that's such a mouthful, we call that PAHdb for short. As you might expect, PAHdb is the focus of the remainder of this talk. What makes PAHdb unique and powerful is that it not only holds the world's foremost collection of genuine PAH spectra, but also provides the necessary software tools and models to work with those spectra. In addition, all of this has been made available through a comprehensive website. It is this trinity that allows users to readily analyze and interpret astronomical observations with PAHdb. In other words, PAHdb offers a complete solution. Next, let's go briefly over each of these PAHdb pillars. The latest version of PAHdb's library of computed spectra contains some 4,223 spectra. That's quite a lot. That of the laboratory spectra 84, and the recently added library of PAH cluster spectra, some 1,030. Though as the histograms on the right show, there are some biases in terms of PAH composition and charge when it comes to the contents of the libraries. However, these biases are slowly being addressed via updates. The distribution to the bottom left shows that the match between the laboratory measured band positions and that of the computed scaled positions is less than 0.5%. Very good, I would say. Moving on to the website is located at www.astrochemistry.org/PAHdb, and it is the place to peruse the contents of the libraries of PAH spectra, download data and software, find support, and use some rudimentary tools. The screenshots here show the landing page, in the back, the browse page, the details page for one of the PAH clusters, and the results of using the online astronomical fitting tool over here. Since its launch in 2010, the PAHdb website has had more than 128,000 daily unique visitors from all over the world. No Google, but I think it's sufficient. PAHdb also offers a number of software tools to work with the spectral data in the databases. The tools are available in both IDL and Python and are being developed, as usual, on GitHub. The screenshots show a rudimentary graphical user interface in IDL. Let's see in the back again. This can be used to peruse the contents of a downloaded database XML file, the results of a database fit using both IDL and Python, with both giving exactly the same result and very assuring, and the results here of analyzing a spectral spatial Spitzer cube to derive a map of the PAH ionization fraction that uses the PAHdb Python tool that we are developing for the PDRs for all JWST early release science program. PAHdb comes with lots of documentation covering all its aspects, from using the website, the software tools, to a cookbook with data analysis recipes. Documentation can be accessed via the PAHdb documentation portal, that's over here, with the web pages being all hosted via github.io. While often falling by the sidelines, we believe a new user's success or failure of using databases often hinges on the valuability of accurate, up-to-date documentation. The documentation is an important thing of developing these type of tools. PAHdb has seen many astronomical applications covering a variety of different astrophysical environments and object types. This includes solar system objects, interstellar medium sources, and of course galaxies. In addition, PAHdb has been used to answer some more fundamental questions about the astronomical PAH population as well. The obvious tagline here is, of course, how would you use PAHdb? One powerful application of PAHdb data models and tools is spectroscopic database fitting. Why one would want to take a spectral database fitting approach can be stated as follows. Spectroscopic assignments are based on spectra of actual aromatic molecules in specific charge states, structures, sizes, and so on. This allows the analysis of the spectra without the need of an ad hoc interpretation of the state of the PAH population, since the average synthesized spectra can be traced back to the fully characterized individual PAH molecules. So the following ingredients are needed in this spectral database fitting approach. First, an isolated PAH emission spectrum. that is, a pure astronomical PAH spectrum with the continuum and emission lines removed and optimally corrected for extinction. Fortunately, there's PAHfit, which we just heard J.D. Smith talk about. Second, a PAH spectral library. Obviously, this is provided by PAHdb. Third, a PAH emission model is needed since the PAHdb provided data are 0 Kelvin absorption spectra. Fortunately again, PAHdb implements a number of PAH emission models in its software tools. Fourth and last, a fitting algorithm. In this case, also again provided by the PAHdb software tools with the choice of a straightforward non-negative least squares fit or a non-negative least chi-squared fit that takes the uncertainties into account. The talk by Alexandro Marokadakis following mine gives a clear demonstration on the spectral database fitting approach. The next steps in the PAH field, and for PAHdb specifically, is to consider the effects of anharmonicity. The computed spectral data in PAHdb has been computed using the harmonic approximation, which assumes equally spaced energy levels, as is shown to the left here. In the anharmonic case, shown here to the right, the energy levels are not equally spaced, and which actually represents what happens in nature better. This figure compares the laboratory measured gas phase spectrum of the PAH anthracene with those computed using a harmonic and anharmonic computational method. Here's the structure of anthracene. Obviously, the goal is to match the laboratory spectrum in the red here as closely as possible. The figure shows that the harmonic spectrum captures much of the overall characteristics of the laboratory spectrum, and that's why we've been able to use it so well on Spitzer and ISO data. However, comparing
about 1 minute remaining.
Comparing the anharmonic spectrum with the gas phase laboratory spectrum shows that the anharmonic spectrum is able to reproduce many of the weaker bands missing in a harmonic one. Furthermore, the anharmonic spectrum captures much more of the subtle substructure of the bands. It goes almost without saying that considering anharmonicity is enormously important for understanding and interpreting JWST PAH spectra. JWST, with its unprecedented sensitivity and high spectral resolution, will readily resolve these anharmonic details. So before wrapping up, I would like to mention that PAHdb has an enormous effort spanning several decades and involving many people. This photo, taken in one of Ames's labs and showing one of the experiments instrumental in measuring PAH spectra, depicts some of these people. That does wrap things up. Please check out the PAHdb website and the next talk by Alexandras, who will provide an excellent use case for PAHdb and galaxy studies. I thank you for your attention.